in this space. We have static over that is that we have static B stage. Jacob here? No. Do you have static?
I do it at my house.
Not walking.
I'm gonna start keeping it on me because
Okay.
see if I ever need for it. That's great.
You should bring for me.
Maybe.
I will.
Maybe
I
if you
forgot
should.
to bring today.
Hey, maybe if you show me the lab.
Yeah. I can help you by plugging out from my.
Oh yeah, I found my sunglasses. They were just they were just in the GTA office.
Oh, great. I also lost my sunglasses, but where
Oh.
I have no idea.
Oh my.
Please not figure out.
No problem.
Go ahead, please.
I will buy another.
I'm helping.
I'll get you some.
I'm helping you in this song.
Okay.
Okay.
No need for publicity.
I'm not going for publicity. I should. Hello. Good. Hello.
Okay, homework, thank you. Is your homework one? You have your homework too?
Supposed to.
The same? No?
Supposed to.
Yeah, Thursday or today if you.
Oh, okay.
Yeah, but if you want to pronounce Thursday is fine.
Should I turn it tomorrow with my?
Okay, yes. It's yours, right?
Yeah.
So your name? Oh, okay, yeah. Okay. Just want to make sure. All right, let's start it. Okay, just brief summarize we discussed so far about the advantage of this variational principle. From that variational principle, we derived this Lagrange equation, and also we extended that to this general Lagrange equation, such that we can, as a summary here, right, we can consider even we do not need to limit ourselves to select these general coordinates must be independent. Yeah, dependent is also fine. So in case of a dependent, even for the holonomic, you can also calculate the force due to the constraint. Same holonomic is this formula here. And in general, with both holonomic, same holonomic, you have both term contribute due to the constraints. We can also estimate or study how this force due to the constraint. So that is the advantage. Then we also discuss to extend to this like circuit, right? So go to the electromagnetic theory or quantum mechanics. So now we want to focus on another important topic from this either variation principle or Lagrange equation about conservation and symmetry. That is the last topic in chapter 2. Conservation theory and symmetry properties of system. Okay, so now go back, so let's consider this case, right? This system is monogenic and holonomic. So in this case, we know the Lagrange equation is here from 1 to n, suppose we have these are independent. Okay, now we are focused on this. So now, since we set up this Lagrange equation, once we know this Lagrangian, that we know how to write this kinetic energy, potential energy, once we set up general coordinates, right? The remaining part is mathematical to solve this equation. So to solve this one, you know it is second order, right? So that is a second order derivative, right? Or partial derivative. Partial derivative. Okay, the partial, difference equation. Partial difference equation. If a second order, you see how many? We have n equations, right? For each equation is a second order differential equation, so you need at least for each one. Okay, just for each one we need 2 integral, right? So actually we need 2n. Okay, integrals. Right? That like 2 initial condition, the initial position, initial velocity at the Newtonian mechanics, if you know. So that is shows that we need. But for this, maybe I mean we can completely integrable. That means if complete integrable for all this 2n, yes, in general maybe you can solve. But in most case, not complete integrated. That means in most cases it's very difficult to solve. So that is, even though we can set up the Lagrange equation, yes, that is not proven. But if you want to solve and find equation motion, that is very difficult. So how to solve it? Okay. Those equations. That is a big job, and that will go to chapters. We are going to discuss this in chapters 8 to 10. And the goal is we try to reduce the second order partial differential equation to the first order. So in the first order, in general, we can do by integral. And also we will introduce the general method or techniques to solve this. So that is the job here. And before that, we want to see even before, so that means before solving, right? Before solving these equations, how much the information we can extract from here? How much the information, or useful information, can we extract this? That is interesting, right? Let's see. Okay, we need to solve this, but before solving that, we probably still can get some or extract most of the important information or useful information from Lagrange equation itself. So in that case, it will also save time for us to solve the equation and also get this sum of the conservation, which quantum conservation and about symmetry. So sum of invariable properties. Those are this we are going to discuss about this topic today. Okay, so one example, let's see here. Consider, right? So consider, let's say, consider a system. If the system is simple, consider a system such that it is a kinetic energy is just a simple summation of all kinetic energy. Capital N is the total number of particles, and then I, okay, x I squared plus y I dot square, and z I dot square, right? That is kinetic energy, and even the potential energy is also the only function of x I, y I, and j I. Suppose then let's write down the Lagrange. Okay, Lagrange is now, look this term, partial L partial x I dot. Just see the Lagrange in respect to, or do the partial respect to the xi dot. Since this xi, yi, ji are independent, right? We just consider independent. So x, y, i, j, I, and x, i, y, i, j are independent general coordinates. So when we do this, you will see only this term. Other does not depend on this, right? So we have m, I, x, I dot. Like this. The linear momentum for ith particle, right? So that means if we know, at least we know the information that if we do the partial derivative with the Lagrange respect to the generalized velocity, in this case, because generalized coordinate is just the coordinate, so that gave a very straightforward linear momentum of the ith particle, right? Okay, so that means we are interested to see this partial derivative partial L with partial, now we, extended to general coordinates. So now, that is, in this case, the particular case, the general coordinates, the position. So in general, let's consider the general coordinates and generalize the velocity in this case. So the Lagrange is a function of general coordinates, general velocity, and time. Then, okay, so now we are going to define this Pj, okay, is partial L with partial Qj dot. That's definition. Here, the Qj dot is nothing but just x dot, so that is the linear momentum of S particle. But here, in general, we are going to define this one because the general coordinates may be the position, translational position, or angles, or some others. Then they associate with this term, maybe linear momentum, maybe angular momentum, maybe some others, right? So now we in general define, give a name as this generalized momentum. Generalized momentum. Or associate, okay, with general coordinates, and we give a code, this is a code, right? Code, give a name, okay. Either called conjugate momentum, or canonical momentum. In from chapter 8, we are going to introduce the canonical variables and the general coordinates and general momentum. They are pairs as canonical variables, and general momentum called the canonical momentum. Generally, we say conjugate momentum. So that's the definition. Now, when we define this, as I said, depend on what type of general coordinate we select. So that's the physical meaning of this depends. So now let's discuss. First, okay. If okay, the Q is position or translational variable. Translation variables. Then Pj is the linear momentum. Okay. General coordinate is angle, and the Pj is angular momentum. Okay, so in general, okay, Pj not be identical to any mechanical or user mechanical momentum. Identical is mechanical moment. Example here. That is because the general coordinates is not angle, not translation. Then in general, the definition of quantum momentum is not usually we say this linear momentum or angular momentum, not usual mechanical momentum. For example, let's consider in this electromagnetic field. Okay, electromagnetic field. So a particle, charged particle, then we have this Lagrangian over many particles. We have first kinetic energy phi, okay? That is MI square. And minus, okay, I from 1 to, again, n particle, we have an electric potential charge, Qi, and potential, which is a function Ri, and plus is the vector field, right, associated with Mach field. That is potential. And from 1 to n. Again, it's charge I, and this is a vector potential with function of R, and inner product is Ri dot. So here this vector potential field, right? Okay, so here, even though this general coordinate is still use Ri, actually you can see Ri over I, X, I, Y, X, I, Y, G, I, right? Still we can use, but the definition now, let's go Pj is partial L, partial Qj dot, right? In this case, partial L, partial R, okay, that's just one of the components. Okay. Then the X, I, dot. So we suppose we select this case, the Qg is Xi. Suppose. Then we look this one. So then you can see here that in the first term we have if it became Xi dot square plus Y dot, so that we have M, I, X, I dot, first term. Second, no, right? Second term does not depend on the Xi dot. This one, the Ri dot is Xi dot plus Y dot plus Z dot, right? So that gives us is the Qi A, okay, AX, right? So here, AX component, since this is inner product. So that is AX Xi dot, AY plus AY Y dot plus AZ Z dot. Then we just do the respect to the Xi dots, only these two terms. So definitely it is not equal to the linear momentum of this ice particle along x direction, right? So that is general. You will see that this cannot say that it's linear momentum or angular momentum or any other. So that's be careful. We just define or introduce this generalized momentum, and this generalized momentum means depend on this represent this momentum is depend on one choice of this general coordinates and also the system. Even though here we select the translational variable as the general coordinates, but the system is in this case, it will not represent this linear momentum. So now be careful. Number 4. Number 4 is more important. Okay, let's look at this one. Let's give the definition, conclusion, and conclusion. So this one is represent the total. Okay. The conjugate momentum of total, not single particle. So here, in this case, it's really just equal to the single particle as component of here. That one as components of linear momentum, right? But in general, like this this is another special case is ice particle, but not the linear momentum. But in general, it gives us a conjugate moment of total system. If system has n particle, right? Total system along QG direction. So how to understand this? Let's see one example, right? So now, example, let's first A. If the Lagrangian is a function of T general coordinate, generalized velocity T, and potential is only function of generalized coordinates and T. Okay, then let's calculate the generalized or conjugate momentum by definition. Partial L, partial Q, T dot, right? Okay. Partial L, partial Q, T dot, and we know here this potential does not depend on the function of Q, T dot. So only this function that is partial T, partial Q, T dot. Now, T. Okay. So T we know. Intermediate step. So partial half of sum over all the particle, right? That is total connectivity of system, partial Q dot. Then here, you will see here, this one, because each R I dot is a function of QG and QG dot, right? So we have to do the partial with respect to R and then do that. So the first this partial RI dot, partial this one, and then partial RI dot, partial QG, right? The partial RI dot, we have a factor 2 cancel, so we have summation I plus 1 to n I RI dot, right? And then partial RI dot, partial QG dot. So you can see here, this will be summation. Sum all terms, right? This inner product here. In general, if not separable, so that this one gives us a sum of all these parts together with respect to the QJ dot. That is the conjugate momentum. So that is a P. This means conjugate momentum represents the total system along this QJ direction. Second one, if the Lagrangian is a function of T minus, okay, T is still function of QG dot, T, and minus in general, the potential is also a function of general coordinates, generalized velocity, like here, right? Like this potential in the electron field on top. So in this case, that's by definition the conjugate momentum, partial L, partial QJ dot, actually is equal to, just for this part, right? But okay, let me just partial T, partial QJ dot minus partial U, partial QJ dot, since U has also function this. So the first term you still can see right on here, like 1 to n, R dot, and the minus here. This one is partial U, partial QJ dot, and what kind of details depend on what the U is, right? So you have also this term. Then you will see here, this is again, we have this summation, so that means the conjugate momentum of total system, not associated with the individual particle. So that is very important. That is in general. Okay, now, so this is to introduce this conjugate momentum. Now, next question, we want to know, once we introduce this, what kind of extra or useful information from here, then we are going to introduce cyclic or ignorable variables, coordinates. we introduce this concept. So first, what does mean? The definition, right? If the L does not depend on QG, then QG is, so definition is very simple. That means L is function of Q1, Qg minus 1, Qg plus 1, but it is it includes this conjugate generalized velocities also include. Only the coordinates does not include. So maybe still have a velocity, that's fine. Okay, sorry, I need to restart. So that's this. Go to Qn, right, lower n, so then Q1 dot, Qj dot, and Qn dot, and T. So only difference here means the Lagrange does not depend on this general coordinate Qj explicitly. Okay, then we call that is cyclic coordinates or this ignorable coordinate. Then okay, now when we define is like we define the general coordinate conjugate momentum, we discuss the behavior, right? So now we are going to also discuss once we introduce the cyclic coordinates, what does mean? Okay, first one. So if Qj is cyclic, so then partial L partial Qj equal to 0, right? Since it does not depend on this Qj explicitly. In this case, then now we go to the Lagrange equation. That equal, because this equal to 0. This only for the particular Qj, right? Not all others. So that equal to d dt partial L partial Qj dot, and that equal to 0. Since we know the Lagrange equation is equal to 0, right? These two terms be equal to 0, and now the second term is 0. So that gives us this. And what that means? C. This is Pg, right? So that total time derivative of Pg is equal to 0. Okay. Okay, so now let's give it. This is the first things we have, and then second one, that means because the partial L partial Qj dot is Pg, so that means dPg dt equal to 0. That immediately got the Pg is constant. Constant means what? Conservation, right? It will not change. So that is the second discussion, the second point we will discuss. Okay, now that is constant, but this is only for, okay, that's it. I just, okay. Only for Qg, not for others. So others, this one does not equal to 0, right? So that's be careful here. Then that is if we consider if the system is monogenic and is holonomic. So if not, in general, so this apply only when the system is satisfied as monogenic and holonomic. Then we have a cyclic coordinates so that we can immediately got this correspond to this conjugate momentum keep constant. So then okay, even for this case, if Qg are not independent. Remember, if not independent, even for the holonomic, we select the Qg is not independent, so this term equal to lambda, summation of lambda partial, remember, okay. since we start from this, so in that case, the d dt partial L partial kj dot minus partial L partial kj is in general, I just begin at the beginning of this class, I already reminded, right? So this term is not equal to 0. Then even though this one equal to 0, it does not mean this conjugate momentum. So be careful here, always discuss the independent general coordinates. If not, it will not. So that is for not independent case. So when we discuss, we first check our the general coordinates whether it is dependent or not, or independent or not, independent. Okay, so now once we have just be careful when we discuss when we introduce the cyclic coordinates, we know what it means. Now we come back to here. This is an important physics or extract the useful information from here. That is, we derive the general conservation theory. Conservation theory. That is the very most important physics or information construct from this Lagrange equation before we solve it. So before solve that, let's look this one. If we have this, you can see that is immediately got this from second order derivative become first order, right? So that is very important information and also solvable for that particular general coordinate. We can have the solution. Okay, so that is. I just repeat. If Qj, now I'm all the independent, right? Independent under this condition. If Qj is cyclic, and of course, independent and the condition, right? And monogenic and holonomic. Those conditions are satisfied, then we have the Pj equal to constant, right? So that means the Pj is conserved under the change. Okay, conserved. That's enough. That is general conservation theory. But here, since this is a generalized momentum, then that is the reason why we say the general conservation theory, because this depends on which general coordinate we select. So here, then we are going to discuss, okay, is this can give us the, from the general conservation theory, we can go to proof in which condition the linear momentum is conserved, in which condition the angular momentum is conserved, right, from this general conservation theory. So we are going to discuss first, right? Okay, primary the conservation for linear momentum. Okay, how to interpret? So now, first, consider, right? If this is a cyclic, then it's a translation coordinate. If its general coordinate Qj is cyclic and also translation coordinates, And now let's see, okay. Consider here this R is a function of, okay, QG, right? And so now let's consider the system. System translates under this QG or around QG. Let's just, since this is translated one around QG. See what happens. So at the QG is here. That is the S particle, the position here. Then after the QG around QG, right? Translate here. So that is Ri, which is a QG plus dQG. Then here, that is translation, that's it. So now here, that is dRi, which is equal to dQg. Since it's along, and give a dQg along this direction, I'm going to give an impact, the unit vector. So that means, let's consider system along the QG direction. The direction is n hat. Then this what happened, the S particle start from QG to QG plus dQg, that is transfer from here. That is dRi, right? So that's with this. Then if this, so now we can look at this partial Ri, partial QG. Since Ri is a function of QG, right? So that is, if we take, we know this partial is the limit of the difference, right? Then dQg go to 0, so then this dQg, and the numerator is Ri QG plus dQg minus Ri QG, right? Mathematically. Okay. So that is nothing but this dRi. So that is limit dQg go to 0, dQg and dQg intact. Since dRi is nothing but dQg along the direction of QG, which is intact. So then, that is, okay. So once we know that, so this is a unit vector, right? Okay, then now let's look this one. Pg is partial L, partial Q J dot, right? Actually, in this case, partial T, partial Q J dot, and release, right? Okay. So then we know that is summation I from 1 to n, and I R I dot. Inner product with partial R I dot, partial Q J dot, right? They already derived. And remember this term? When I introduced general coordinates, I already gave this, have this very important relation. So that is, let me just continue here. That is I from 1 to n, m I r I dot, inner product partial r I, partial qj, right? Partial r I dot, partial qj dot equal to partial r I, partial qj. Then here, partial r I, partial qj is in hat, right? So that is, that is summation I from 1 to n, m I r I dot, inner product in hat. And if inner product in hat means the Ri dot project to this direction, right? So that is, if I'm going to say Pn. So that means if somehow all the momentum, there's a linear momentum, all the particle has a linear momentum and project to the n direction. Which n direction? Qj direction. So that is this one. This gives us the total, the conjugate momentum of total system, right? Not this individual heat summation. So that is or linear momentum. Okay, let's see. Of total system along or project. Let's see, project. Project to QG direction. So you can see here, this general conservation theorem gave us. Now we have not okay. So since okay, so we have since we already since QG is cyclic, so we have a Pn equal to constant. That is nothing but the conservation of linear momentum, right? So in general, this linear momentum should be the linear momentum of a total momentum. The complement of total system, not individual. That is very important. Along or project, projected to QG. So you can see here, if we extended this general conservation theorem to the case when this cyclic coordinate is translational coordinates, what happened? It will tell us the linear momentum of a total system project to that direction is conserved, right? That is the key information here. Second one, how to interpret okay, the conservation for every momentum. Angular momentum. Again, we still consider QG as cyclic and its angle, rotation angle. Okay. This is a rotation. Represent a rotation. About some axis and still use in hand. Okay, so now let's see here. This is the axis in height. Okay, then we do the rotation, right? Okay. Then here, so here this is R. Highest particle, this real position is a function of QG. And then after rotation, delta QG or dQg. So here we go to this direction, DRI, right? Then I hope I could not. This is a RI QG plus dQg. Busy here. So now let's do busy and here this one is QG, right? And this one is dQg. Okay, so that is represent the dQg is represent a kind of rotation about the axis, some axis direction give n hat. And what happened? Let's look at S particle. Initially, with QG is this position, then QG from QG plus dQg is just rotated to this position. So that is This is the DRI, right? So now we are going to see absolute value of DRI. This one, we know is this, multiply this one, right? Is RI sine theta Q, G, right? So RI is this one, and RI sine theta is this length, right? This length multiplied with this distance, right? So that is the DRI. Therefore, let's look at this absolute value of a partial RI, partial QG. That's B. Here, okay, is okay, is RI sine theta and absolute value. So that is this RI sine theta, and then this direction. You can see this DRI. This is this part, right? So that is a cross product of RI. N, right? N cross product to RI, and let's go to this direction, DRI, right? So that gives us this one. So that is this absolute value, and that gives us the partial RI, partial QG is equal to the cross product of N type with RI dot. This one. Right? But this is a very small, so this is perpendicular. So that is cross product, right? So that is the analysis of partial RI with respect to QG. Then once we know this, we are going to look. If it is cyclic, then they are associated with the conjugate momentum. What is the conjugate momentum? So if the Q, let's look at QG first, right? So the PG is partial L, partial QG. That is, again, we have that one, right? Here, this guy. That is I from 1 to N, M, I, R, I dot. Partial R dot, partial QG dot. And we will replace dot inner product of a partial RI, partial QG, then that is NI dot N cross is RI, right? That is the step. So now, here we have not yet seen the detailed physics here, but you see, this is a vector, inner product is a cross. So that equivalent, we do this cycle, right? So that equivalent, if I do the cycle, then that I make the N hat inner product with, so that is here, Ri go to fund, right? Do the, like this counterclock cycle. You know that, right? Okay. Cross R dot. And this go to here, and this go to fund, right? That is this equivalent. And now you can see here, that is N I dot, and now summation I from 1 to N. What is one? Mi multiply Ri dot is momentum, right? So that is Ui. If I use this angular momentum of each particle, right? So okay, maybe I write down here. In Ri here, and I move this Mi to here, cross Mi dot. This one is Pi, right? Linear momentum of each, that's the physics, each individual particle. And then the Ri cross product is angular momentum of each one. But now, linear product to the along only project along that axis, right? So that is Ln. Okay, so Ln, that is this angular momentum of the total system project to a direction, or QJ direction. QJ is we define this rotation with axis in. So here, so then if QJ is cyclic, then we have immediately get this Ln is constant. That is conservation of so you can see it really depends on the choice of general coordinates, the physical meaning or associated physical meaning of this generalized momentum. It may be total linear momentum, our linear momentum of total system project to given direction, or the angular momentum of total system project to given direction which conserve. Okay, with this conservation, then we are going to discuss very interesting associated with this. So now you can see what the relation between the conservation, Ln equal to constant means this be cyclic. The Pn, this constant means this must be cyclic, right? So that's have some relation. And what does mean cyclic? That is the symmetry, the relation of symmetry and conservation. They always connect each other. So when we say conservation of some of physical quantity associated with symmetry of system. So what that means? Okay, let's say okay. So now let's see. If right, consider this is so far if Qj is cyclic of Lagrange. So what does it mean? Lagrange is physics system, right? System. So that means the system is invariant or invariant under the change of Qj, right? That means. So when we say cyclic, what does it mean? Since cyclic is Lagrange does not include, right? L equal to L, if I write down again, Q1, Qj minus 1, Qj plus 1, and others. And all is Qj out. Nothing includes, so whatever will change, it will not change, right? That is system. So the system is invariant under this, then that leads to that, to which we have this conclusion. So what that means? Conservation. Right? Conservation of theory. So you see the relation. That means this environment symmetry. If not change, that means the system has a symmetry with respect to this cyclic coordinates. Since the cyclic change, system will not change. So system has such symmetry, then that must be associated with a physical quantity we call general coordinates, general momentum, which is constant. So that is conservation. Okay, now let's give us the relations between this. So now I'm going to say if Q is a cyclic, like for example, if Q is a translation, then the conservation theorem tell us linear momentum, right? But it is of total, okay? This is important. Total system project around. So, okay, that is cyclic, that is symmetry right here. That means symmetry. Okay. So if you compare the relation, the symmetry and conservation, then if the QG is cyclic, that means this is a system will have a symmetry respect to this one. If this is a translation, that implies there is a conservation of total linear momentum of the system project to this direction. If this is a rotation, if this is cyclic coordinates is a kind of rotation, that implies there's angular momentum, right? Angular momentum of the system projects along the axis above axis. QG, right? So above that QG we have rotation, and that is the project. Let's see, project along. Okay, the axis of QG. Let's say this one. So now, if this is others, okay, what is others? We will discuss one after this. So that gives us, you see, that always have the symmetry, and associated with symmetry always have the conservation, one of the principal quantities conserved. Okay. Now when we say others, now let's consider one of these very important information about others. Okay, here we know the linear momentum or angular momentum. These are mechanical or momentums which we know associated with this translation or rotation. How about energy? Energy is also one of important. So now we are going to see the others is energy conserved. Then associated with energy, what kind of QG corresponds to energy? Okay, let me write down this one. Others. So now others, for example, which kind of QG which correspond to energy? Right? Think about this. Okay, so now we are going to discuss this. Or extend this general the conservation theorem to in more general to the system of energy. Okay. So now let's consider this. Okay. Consider Lagrangian is a function of general coordinates, general velocity, and t, right? Consider this. And then now let's look at the total time derivative of Lagrangian. So total time derivative, we know first QJ dot all are function of time, so we need sum over OJ from 1 to n and partial L, partial QJ and QJ dot, right? And plus J from 1 to n and partial L, partial QJ dot, QJ double dot, right? Okay? And increase this part. Another term, T, right? If the Lagrangian also depend on time explicitly, so we have partial L, partial T. So that is total time derivative of the Lagrangian. Okay. Now we are going to study this, and we will see their associated with energy. So now, because since so far from now on, we always focus on the monogenic system with a holonomic condition and with the general coordinates are independent, right? So we always use this formula. When we use this, that imply, right? Imply the system is monogenic. The monogenic means the force is always the derivative of the existent scalar field, right? And constraint always holonomic, so that we can find the independent general coordinates. So that is okay because it's. So we have. Now we are going to find this relation, right? So the relation is partial L, partial QG. If I move to the right hand side, that is total time derivative of partial L, partial QG dot. Then I'm going to sub into here. So total time derivative of Lagrangian is equal to, okay, the partial L, partial QG is total time dt, partial L, partial QG dot, multiplied QG dot, right? And I keep the same, the second term and third term I keep. So I keep here. Partial L, partial QG dot, double dot, partial L, partial T. Now look at the first and second term. If I direct write down here, the second, okay, let me write down here. Hope you understand that. Is the total time derivative of this product, partial L, partial Q, J dot, and Q, J dot. This term, let's look, if this product, so then we do the total time derivative first, do this one, double dot, right? That is the second term, this one. And then second one is keep, do this one, sorry, we don't. Oh, yes. First, keep this one and do this. That is the first term, right? Total time derivative this one. And then second, keep this one and do this. So that is this one double dot. So that is this. Then this total time derivative term. I'm going to move to the right hand side since this one also total time derivative, right? So then the total time derivative of L, this one, minus summation j from 1 to, okay. Let's do this one. Just check, so that means I'm going to move this to the left hand side and that one to the right hand side, so that is minus partial t, that's it. I'm going to move this up, but this one to this one, so we have total time derivative, this positive, summation j from 1 to n partial L, partial Q, j dot, Q, j dot, minus L, right? I move this one to the right hand side, so I have a minus L, and move this term to the right hand side, left hand side. So I have this. Now you see, this is a total time derivative of sum of function. So I'm going to introduce or define h, which is a function of this term. We call with a name energy function. Okay. If this energy function, and you know that's the function of Qj naught, and time, right? Since this Lagrangian function Qj naught and time, right? So then we have introduced, then this formula is give us dh, total time derivative of this energy function is equal to the negative partial L partial t. Very important information comes here. So now we are going to discuss what does it mean. we introduce energy function does not mean it is energy. Now be careful. So this is also called the Lagrange integral here. Sorry, Jacobi. Energy function is of course Jacobi integral. Okay, now we discuss. We introduce new quantities, so now we are going to discuss what this means. Okay. First, if the partial L partial T equal to 0, and that's the most case, yes, right? Lagrange does not depend on time explicitly, then immediately we got this total time derivative of energy function is 0, so energy function is constant. That gave us a conservation of H, but not energy. So when we look this Lagrange does not depend on time explicitly, we immediately know there's energy function or Jacobi integral. It is constant, so that is the first thing. Second, as I mentioned, if you're not, so in general, right? H does not depend on energy, only under certain So now we are going to discuss this. So what that means, if H not equal to E, even though H constant, energy does not mean constant. Does not mean energy is conserved. So we have to discuss the condition for, so what is the condition now? That is the second key, right? Now we are going to discuss conditions for H equal to E. Hopefully, I don't think we can finish today, but we'll continue, keep continuing on Thursday. So now let's consider that. Because T is function of, is, okay, that's T, summation all the particle, Mi, half, R, I, dot, square, right? And this one, and Ri dot, okay, is total time derivative of Ri with T, right? And Ri is a function Qj, so that means J from 1 to n, partial Ri, partial Qj, and Qj dot, plus partial Ri, partial T, right? That is in general. So we are going to substitute this into here. So T is equal to half of I from 1 to n, mi. Now I'm going to put here, right? So that is summation j from 1 to n, partial Ri, partial Qj, Qj dot, partial Ri, partial T, and inner product with another, right? But the summation, since we need to make a different, so k from 1 to n, then partial Ri, partial Qk, Qk dot plus partial Ri, partial T. So we have a totally 4 terms. Now let me write down the 4 terms and we are going to discuss. Okay, keep the half here. Summation I from 1 to n, mi. Okay, now the inside, first one is summation j from 1 to n, summation k from 1 to n, and then it's a partial Ri, partial QG, inner product partial RI, partial QK, QG dot, QK dot, right? The first term. And the second is cross term. Okay. Cross term, so they have two, since the cross the same, right? So we have, okay, let me. Okay, let's keep it. That's four terms, so now second term and third term, right? J from 1 to n, partial Ri, partial QG dot, and partial, and multiply the inner product partial Ri, partial T, right? This one to, and then this third term is summation K from 1 to n, and the partial Ri, partial QK, QK dot, and then the product partial Ri, partial T. The last one, that's right up here. Last one is partial Ri, partial Ri, one is T. So that is just square, right? Partial Ri, partial T, square. Okay, let me just finish this term and then we can stop here. So now the first term, we have a summation I from 1 to n half, okay, and then the half is, now let me do, just jump to in the middle. So now, let's put the last term as a first term now, because that does not depend on QG dot. So I'm going to write the last one as the first one, summation I from 1 to n, half of mi, partial Ri, partial T squared. And the second one, these two terms, you just see just summation different, right? So they are same, so we can combine together. Then half became 1, right? So that the second one is I from 1 to n, mi, okay? And then the summation j from 1 to n, partial Rn, partial qj dot, right? Yes, sorry, inner product of, inner product partial Ri, partial T, qj dot. Did I miss that one? I think, yeah, right, partial T. And then this first term become last one, plus, so we have a still half, right? Summation I from 1 to n, half of mi, partial Ri, partial qj, partial Ri, partial qk. Oh, two summations, sorry. Two summations. Summation j from 1 to n, summation k from 1 to n, partial Ri, partial qj, inner product partial Ri, partial qk, and qj dot, qk dot. Then you see I have three terms. I'm going to say T1, T0, T1, and T2. Okay, let me stop here. T1 you will see is 0, zeroth order of qj dot, and T1, T0. T1 is first order, right? And the T2 is the projector. So when we finish, distinguish this in this way, we will find the condition in which way this is equal to energy on Thursday. Okay, I think I forgot to, but I already mentioned in the Blackboard, right? Midterm, exam, on Thursday I will give, right? So Thursday, we deliver on Thursday, and the term, let's say, is start, right? Starts on Thursday, and turn back on, that is another, next Thursday, right? Next week. And take it home so that the chapter 1 and 2. So we definitely will finish chapter 2 on Thursday. Those topics, for example this, all will go to the midterm exam. Okay. Double check. So do you have your homework to do? Not finished?
Shall I?
Yeah. I mean, you mean on Thursday, right? You want to?
No, tomorrow I can.
Tomorrow.
Yeah.
Okay, tomorrow. Yes, fine.
Quantum one, right? Okay. Oh.
No, this.
That
this,
one I totally
sir,
forgot to.
You forgot.
Yeah, I got the wrong book actually. That's.
Okay. So maybe tomorrow you find it. Yeah.
I'll
Quantum
handle
and-
both
yeah,
of them
yeah.
tomorrow.
Okay. Good.
Oh. This midterm paper, we can submit in person or in Blackboard.
You submit what?
Yeah, submit this midterm answer sheet.
You mean the lecture notes? What do you say?
That midterm exam.
I
is
will.
a
Yes,
take-home
post
and-
on definitely. I will post on Blackboard.
Yeah,
And
our
also-
answer should be posted in Blackboard or we can submit. In
You mean the midterm exam?
Yeah.
If you post, I have to also print out. If